Welcome back to the deep dive. Okay, today we're tackling something really core, maybe a bit dense, but it's the absolute foundation for modern AI. The math underneath it all.
That's right. We've got these detailed lecture notes focusing on linear algebra and how it actually gets used in machine learning.
Yeah, and if you really want to get how AI learns, well, this is the engine room, isn't it?
It really is. And our job today is basically to cut through the jargon, give you a clear map of the key ideas, the concepts that let these algorithms work.
So where do we start?
We start right at the beginning with this framework the sources lay out. It's simple but powerful. Learning, representation plus evaluation plus optimization.
Okay, representation, evaluation, optimization. That sounds like a roadmap for almost any learning task.
It pretty much is. Representation is just, well, choosing the language. What kind of functions can the computer even learn? Is it thinking in straight lines, curves, something else?
Got it. Then evaluation. That sounds like grading its homework.
Exactly. It's the objective function, the scorecard. How do we measure if it's doing well or poorly? What counts as a good answer?
And finally, optimization. That's the learning part.
That's the search. It's the actual method the algorithm uses to find the best settings, the best parameters within that chosen language to get the highest score on that evaluation. It's the engine driving the whole thing.
Okay, let's make this concrete. Simplest case, linear regression. Predicting a value, like a price.
Right. The machine starts by trying to fit a straight line, and that line is defined entirely by its parameters, its weights, the verpal.
Those weights determine the slope and where it starts on the graph, the intercept.
Exactly. And one of those weights, theta naught, is the bias. It's like a baseline prediction even if all your inputs are zero. Finding the best set of those weights, that's the whole game.
So, okay, the machine picks some weights, maybe randomly at first. How does it know how far off it is? How does it evaluate?
Good question. That takes us to evaluation for regression. The standard approach is squared error loss.
Squared error. So you take the real answer, subtract the machine's prediction.
And square the difference.
Why square it?
Well, two reasons, really. One, it makes all errors positive, so they don't cancel out. A negative error is still an error.
And two.
It penalizes big mistakes much more heavily than small ones. Being off by 10 is way worse than being off by 1 squared.
Right. It really pushes the model away from those huge misses.
Precisely. And when you add up all those squared errors for every single example in your data, you get the total cost function.
J of theta equals 1 over 2m times the sum from I equals 1 to m.
Okay, the setup.
Of the quantity AGH theta of x superscript I minus y superscript I squared.
Optimization is just finding the value that makes this total cost as small as possible.
Okay, but the real world isn't always straight lines. What about curves? Data often curves. How does AI handle that if the tools are based on linear algebra?
This is the first really clever conceptual trick. Polynomial regression. You want curves. Fine. We generalize the function.
But doesn't that mean throwing out the linear math?
Nope. And this is the beauty of it. It handles the curve by sort of pretending. It treats powers of the input, up to some degree, as if they were totally new, separate input variables.
Oh, I see. So the equation looks curvy if you plot it against the original sixtiles, but in terms of the parameters, the vectors you're solving for.
It's still linear. It's still just a weighted sum of terms.
So the math for finding the best weights doesn't fundamentally change. That's actually pretty elegant.
It's a huge computational advantage. Finding the best fit for even a complex curve boils down to solving a system of linear equations, which we're good at.
Okay, the math seems solid, but let's talk about a potential trap here. We're minimizing error on the training data, the data we have now. Is that really the end goal?
No, absolutely not. And this is maybe the most important concept in practical ML, generalization.
Yeah.
Meaning the model has to perform well on new data. Data it's never seen before during training. Just doing well on the training set isn't enough. It might just be memorizing.
So there's a conflict. The machine needs to find the real pattern, the underlying signal.
While ignoring the random noise, the little quirks that are specific only to the training examples.
But how can it possibly know which is which? Signal versus noise.
It can't, not inherently.
Yeah.
And that leads us straight into the classic problem, overfitting. Imagine the true pattern is a smooth green curve, but your data points are scattered around it because of noise.
If you fit a simple line, or maybe a gentle cubic curve, degree 3, it might miss some noisy points, but it captures the basic shape of the green curve.
Right. It generalizes reasonably well. But now, imagine you use a really high-degree polynomial, say degree 9.
It would wiggle like crazy to hit every single data point perfectly, right?
Exactly. It gets a training error down to almost 0. Looks great on paper, but it's modeled the noise, not the signal.
So when you show it a new point that wasn't in the training set,
its prediction will likely be miles off.
yeah,
It's completely useless for generalization.
it's like that student who just memorizes the textbook, typos and all, scores 100% on the practice questions, but hasn't actually learned the concepts.
Perfect analogy.
Mhm.
That's why we look at metrics like root mean square error
Yeah.
on separate test data. It helps us see if the model truly learned or just memorized. You have to find that balance.
Okay. Super important concept. Now, let's shift gears. We've been talking about predicting numbers regression. What about predicting categories, like yes, no, spam or not spam?
Right. Classification. This is hugely common. Malignant or benign tumor. Is this picture a cat or a dog?
The challenge here seems different. Our output can't just be any number anymore.
Exactly. For classification, especially binary two-category classification, we need the output to be a probability. It must be between 0 and 1.
A straight line from linear regression goes off to infinity. It doesn't respect that 0 to 1 boundary. So how do we fix that? How do we squash the output?
We use another clever function. The logistic function, often called the sigmoid. Think of it as a mathematical squisher.
The S-shaped curve.
That's the one. It takes any real number input, no matter how large or small, positive or negative.
And smoothly maps it into that range between 0 and 1.
Perfect. So we calculate our usual linear combination, zec dot, but then we feed that result into the sigmoid function.
And the output of the sigmoid, we interpret that as the probability.
The probability that the example belongs to class 1. So if it outputs 0.7, we say there's a 70% chance it's, say, spam.
And then we just need a threshold. Like if it's above 0.5, call it spam.
Usually, yes. And that threshold point defines the decision boundary.
That's the line or curve, potentially, that separates the two predicted classes in our feature space.
So we still have a linear boundary, but we use the nonlinear sigmoid to get a probability interpretation.
Okay, we have probabilities now. Can we just go back to using our old friend, the squared error loss function, to evaluate how good these probabilities are?
You'd think so, wouldn't you?
Mm.
But no, if you try to use the squared error loss with the sigmoid function plugged in, the math breaks down for optimization.
Breaks down how?
The resulting average cost function becomes non-convex.
Non-convex. Okay, what does that mean practically? Why is that bad?
Imagine the cost function as a landscape, and you want to find the lowest point. A convex function is like a simple bowl. There's only one bottom, and no matter where you start, if you always go downhill, you'll find it.
Okay, simple enough.
But a non-convex function is like a landscape with lots of hills and valleys. There are many little dips, locominima, that aren't the true lowest point, the global minimum.
So our optimization algorithm trying to go downhill could easily get stuck in one of those small valleys.
And if it's found the best answer, when the actual best answer is in a much deeper valley somewhere else, it gets trapped.
And we can't have that. We need to reliably find the best set of weights.
We absolutely do. So we need a cost function that guarantees a convex bowl shape.
Which leads us to the specific cost function used for logistic regression. It looks a bit scary, involving logarithms.
It does, but the intuition is actually quite neat. It works in two parts.
What's the gut feeling behind using logs here?
Think about the penalties. If the truth is log as 1, but your prediction log gets close to 0, meaning you're very confident, but very wrong.
Log of a number near 0 goes to negative infinity, so negative log goes to positive infinity.
Exactly. The cost skyrockets towards infinity. It massively penalizes being confidently wrong.
So it puts huge pressure on the algorithm to fix those really bad confident mistakes. And if the prediction is perfect...
The cost is 0, no penalty if you're perfectly right.
Clever. And this specific log-based function is convex.
Yes, mathematically, it's guaranteed to be convex, meaning our optimization algorithms can reliably find the single best global minimum. Problem solved.
Okay, brilliant. One final jump in complexity, but it's essential for pretty much all modern deep learning. Tensors, what are they?
Well, in simple terms, a tensor is just a generalization. It's what you get if you keep adding dimensions.
So a single number is a scalar, like an order 0 tensor. A list of numbers, a vector, that's 1D, an order 1 tensor.
Right. A grid of numbers, a matrix, is 2D, and order 2 tensor.
And a tensor can be 3D, 4D, or even higher dimensions.
Exactly. A 3D tensor is easy to visualize as a cube or a stack of matrices. A 4D tensor could be like a list or vector of those cubes.
And this is useful because data often has more than 2 dimensions, right? Like an image.
Perfect example. An RGB color image has height and width. That's 2 dimensions. But then it also has the depth for the red, green, and blue color channels. That's inherently a 3D structure.
So a 3D tensor is the natural way to hold that image data.
It is. Tensors are basically the standard way we represent multidimensional data in libraries like TensorFlow or PyTorch.
And basic math, like adding two tensors or multiplying them element by element, the Hadamard product.
Usually pretty straightforward. You just do the operation on the corresponding elements, assuming the tensors has compatible shapes. Element-wise, addition, subtraction, multiplication, division, they work as you'd expect.
But that's different from the tensor product.
Very different. Element-wise operations keep the dimensions the same. The tensor product fundamentally increases the dimensionality. For instance, the tensor product of two vectors, order 1, actually gives you a matrix, order 2. Understanding that difference is pretty key later on.
Wow, okay. So let's recap. We started with that core framework: representation, evaluation, optimization.
Right. Then we saw how linear algebra forms the basis for prediction with linear regression, finding those optimal weights.
We saw the trick for handling curves, using polynomial regression, keeping things linear in the parameters.
Then the critical concept of generalization and avoiding overfitting, not just memorizing the training data.
We switched to classification, using the sigmoid function to get probabilities between 0 and 1.
And crucially, adopting that special logarithmic cost function to ensure we could actually find the best parameters reliably, avoiding those nasty local minima.
And finally, we generalized our data structures beyond matrices with tensors, the language of multidimensional data.
And the big connection here is that these fundamental building blocks, especially linear and logistic regression math, they aren't just historical footnotes. They are essentially what happens inside each node of a modern artificial neural network.
Right, the core operations repeat over and over. But here's the final thought, the cliffhanger maybe. We've talked a lot about the what's minimizing this cost function, finding the lowest point in the landscape. But we haven't really talked about the how. How does the algorithm actually find that minimum? How does it navigate that complex landscape in practice?
Yeah, that's the next piece of the puzzle. And the sources definitely point towards calculus, derivatives, gradients, the chain rule.
So if the cost function little Orofana is our mountainous terrain,
then the math we talked about today defines the shape of that terrain. But calculus gives us the map, encompass the specific steps, the path called gradient descent, that the algorithm takes to actually walk downhill and find the bottom.
the path to the optimal parameters.
Yeah.
Fascinating. Well, we've mapped the landscape today. Next time, maybe we learn how to actually walk it. Thanks for joining us on this deep dive.
Absolutely. Keep pondering that difference between fitting the data and truly generalizing. It's key.